So you are able to hear me? Are you able to hear me? Oh, actually, I dropped my wired earphones on my lab, so I had to connect through my phone. That's why it got a bit delayed. I'm sorry for that. Yeah, that's right. No, two logins, one in my phone and one in my laptop, actually. The other one, I think the presentation is showing as the third login. Yeah. Okay. Yeah. So last class we stopped over here. In this problem, we were considering two perfectly absorbing isothermal atmospheric layers. So today, I think we will start from deriving the equation for this condition. And there are two perfectly absorbing isothermal atmospheric layers. Yeah. So suppose this is the Earth's surface. Okay, I'll just read out the question once. So the question was the mean emission temperature of a planet is 280 Kelvin. It has two perfectly absorbing isothermal atmospheric layers. What is its surface temperature? So that was the question. So in the question, the emission temperature of the planet is given, which is 280 Kelvin, which is basically what is being emitted from the top of the atmosphere. And they are asking what is the surface temperature, which is Ts. And about the atmosphere, they are telling like the atmosphere is basically two layers. Both of them are perfectly absorbing. Suppose this is the incoming solar radiation incident on the surface of the Earth. After it reaches the surface starts re-emitting the radiation, which is given by yeah, which is given by sigma Ts raised to 4. So this is the surface temperature, the radiation that is being emitted from the surface. So the surface emits a radiation of sigma Ts raised to 4. And now we have two isothermal atmospheric layers. So as you said in the last class, isothermal atmospheric layers in the sense two layers which is isothermal within that particular layer, which is having different temperature. So within those layers, the temperature is a constant, but we have two layers with different temperatures. Let it be T1 and T2. So suppose sigma Ts raised to 4 is the radiation. Yeah, that is the radiation that is being emitted from the surface. And as it is said in the question, both the atmospheric layers are perfectly absorbing, which means it will take up all this sigma Ts raised to 4 radiation and it will re-emit radiation in both directions, which is given by sigma T1 raised to 4, where T1 is the temperature of this particular layer. So this is the emission from the first layer. Now, to the second layer, sigma T1 raised to 4 is the radiation that is going to the second layer. And after absorbing this particular radiation, again, this layer will start re-emitting radiation in both directions, which is given by sigma T2 raised to 4 and sigma T2 raised to 4. Now, the radiation that is being emitted from the top of the atmosphere, so sigma T2 raised to 4 will be equal to sigma T raised to 4, which is the emission temperature. So we can write T2 is equal to TE. So T2 is equal to the emission temperature that we are considering now, which is given in the question, which is 280 Kelvin. Now let's see what is the relation between Ts and T2. So let's start with the surface energy balance for the layer 1. So energy balance for layer 1. So for the layer 1, the incoming radiation is sigma Ts raised to 4. Like we'll start with layer 2 so that we'll get the relation between T2 and T1 first. Yeah. So in case of layer 2, the incoming radiation is sigma T1 raised to 4 and the radiation that is being emitted from the surface is sigma T2 raised to 4 in both the direction. So we can write sigma T1 raised to 4 is equal to 2 sigma T2 raised to 4. In case of the second layer, we can write sigma T1 raised to 4, which is the incoming radiation, is equal to 2 sigma T2 raised to 4. Correct? The radiation that is incoming to the second layer is sigma T1 raised to 4. And the layer 2 is absorbing this radiation and it is re-emitting in both the directions. So sigma T2 raised to 4 upwards and sigma T2 raised to 4 downward. So this is the energy balance for layer 2. From this, we can write the relationship between T1 and T2. So from here we can write T1 raised to 4 is equal to 2 to T2 raised to 4. Or we can write T1 is equal to 2 raised to 1 by 4 into T2. We already know that T2 is basically the emission temperature. So you can write T1 is equal to 2 raised to 1 by 4 into TE, which is the emission temperature. So let this be relation number 1. Now let's write the energy balance for layer 1. So for the first layer, just this particular layer, there are two incoming radiation that the layer is absorbing. One is this sigma Ts raised to 4, which is coming from the surface. And the second one is the sigma T2 raised to 4, which is coming from the second layer to the first layer. So two from both directions, this layer is receiving radiation. One is the sigma Ts raised to 4, which is coming from the surface. And the second one is the sigma T2 raised to 4, which is being emitted from the second layer. This is also reaching there. So two incoming radiation is there. So we can write sigma Ts raised to 4 plus sigma T2 raised to 4 is equal to, and the radiation the layer is emitting is sigma T1 raised to 4 in both the direction, which is 2 sigma T1 raised to 4. So we can write sigma Ts raised to 4 plus sigma T2 raised to 4 is equal to 2 sigma T1 raised to 4. From this, we already know that T1 raised to 4 is equal to 2 T2 raised to 4. So if we substitute this in this equation, we will get everything in terms of T2. So sigma Ts raised to, we can cut all these sigmas as well. So Ts raised to 4 plus T2 raised to 4 is equal to 2 into 2 T2 raised to 4. Or we can write Ts raised to 4 is equal to 4 T2 raised to 4 minus T2 raised to 4. Or Ts raised to 4 is equal to 3 T2 raised to 4, which basically implies Ts is equal to 3 raised to 1 by 4 T2, where T2 is basically our emission temperature, which is T. So this is the equation where when we have two perfectly absorbing atmospheric layers. So the relation between Ts and the emission surface temperature and the emission temperature when we have two perfectly absorbing atmospheric layers is Ts is equal to 3 raised to 1 by 4 into T epsilon. So if you want to generalize it into n perfectly absorbing atmospheric layers, you can write. So the derivation is the same. You just have to increase the number of layers. So in that case, it will become n plus 1 into 1 by 4 into T epsilon. So this is in case of n perfectly absorbing atmospheric layers. So this is the derivation is the same thing. If you increase the two perfectly absorbing atmospheric layers to 3, you will see how it is kind of progressing. So the generalized expression will be Ts is equal to n plus 1 the whole raised to 1 by 4 into Te. Now coming back to our question. In our question, the mean emission temperature is given, which is 280 Kelvin. And in this case, we are considering two perfectly absorbing atmospheric layers. So the equation that we got is Ts raised to 1 by 4 is equal to 3 raised to 1 by 4 into T epsilon. So here we can write Ts is equal to 3 raised to 1 by 4 into T epsilon. T epsilon is having a value of 290 Kelvin into 290. So what will be the value? 290 or 280? Yeah, 280. Yeah, 280 Kelvin. Yeah. So what will be the value? Yeah. So the answer is 368 Kelvin. So we have derived the equation for we know in case of if we are considering perfectly absorbing single atmospheric layer, in that case the equation was Ts is equal to 2 raised to 0.25 into T epsilon. And in case of partially absorbing single atmospheric layer, the equation was Ts is equal to 2 by 2 minus F into the whole raised to 0.25 into Te. Now we derived for perfectly absorbing two atmospheric layers, or in a more general form, n perfectly absorbing layers. Ts is equal to n plus 1 the whole raised to 1 by 4 or 0.25 into T epsilon. So these are the different equations that we derived and we found out. And if we don't have an atmosphere, what will be the relationship between Ts and Te? Can you tell me? In case of no atmosphere, how it will be? Yeah. So in case of no atmosphere, Ts will be equal to T. So these are the different conditions. Okay, I hope it is clear. Yeah. Yeah. So now the next question is the Earth's mean black body emission temperature is lower than the surface temperature. So the statement is TS is less than TE. Is this true or false? So we have already seen like in case of Earth, we have been deriving. So in all cases, we were getting like some number raised to 1 by 4 into TE. So this was the relation that we were getting for TS. Yeah, no, no. The Earth's mean black body. Okay, I think I wrote it. Earth's mean black body emission temperature is lower than the surface temperature. TE is less than TS. In that case, it's true or false. So if we take the most simple case, 2 raised to 0.25 is basically a value which is less than 1. So which means which one will be greater? Is it? Yeah. TE is basically greater than. Yeah, it is 1.18. Greater than 1. Yeah. So T is coming to be greater than TS. So this is false. Okay. Now, TS is always greater than TE. Yeah, surface temperature is always greater than. Uh-huh. Sorry? Yeah, yeah. Yeah, TS is always greater than TE. So this is correct, no? Okay. Yeah, Earth's main black body emission temperature is this is true, right? The question. Yeah. Yeah, TS is greater than TE. That's correct only. Yeah. Okay. It is true. I got confused in between. So yeah, the mean albedo of Earth remains constant throughout the year. Is it true or false? So we know we have a global mean albedo. What is the albedo of Earth that we generally use in equation? Yeah, 0.29. So is yeah, it is not constant. So what all things actually um, changes the albedo of the Earth? It depends on what all factors. Mm. Mm-hmm. Yeah. So yeah, it depends on seasons and latitudes. Which latitude we are considering? Polar, tropics, subtropics, all those regions. And yeah, and the land cover type also like ocean, desert, forest, and all those things. So basically, albedo is the fraction of solar radiation that is reflected back by the Earth. The fraction of solar radiation that is being reflected back by the Earth is basically given by albedo. The absorbed solar radiation of the Earth, yeah, yeah. It basically depends upon the albedo of the Earth. So if E absorbed albedo is given by incoming solar radiation, which is ES into 1 minus alpha. And you were asking why we are using this notation of dot on top, E and dot. So this is basically because we are dividing, this is basically per unit area per unit time. So D energy per unit area per unit time. So in order to notate like this, in order to indicate that it is giving per unit area and per unit time, we are using this dot. It is a derivative with respect to area as well as time. So that, yeah, so that's why we are using dot. So E absorbed is basically given by if ES is the incoming solar radiation and alpha is the albedo, absorbed solar radiation is given by ES into 1 minus alpha. And as we already said, the mean albedo of Earth is given by 0.29, but the value varies with respect to latitude and seasons. So alpha varies with latitude and season. So albedo is generally the highest. The highest value of albedo is seen over regions which are having very high cloud cover or also where there is high ice or snow. So with respect to latitude, if you look, the regions which is having very high cloud cover is over the equatorial regions, and the regions which are having very high ice or snow is basically the polar regions. And if you look at the seasons, during winter season, generally the northern hemisphere is mostly covered with. We have like more ice and snow conditions. So if you look at the albedo over the polar regions, polar albedo is having values close to 0.8 to 0.85, and the equator, which is having very high cloud cover, and over the equator, due to the high cloud cover, the values are 0.4 to 0.45. And lowest albedo generally occurs is highest albedo. Yeah. Which region can you tell me if you are looking with respect to latitude? Which region will be having the lowest? Tropical is having very high cloud cover, as we were saying. So the subtropical region are generally characterized with, yeah, subtropical region is generally characterized with low cloud cover because there is sinking motion over those regions generally. So because of that, the subtropical ocean regions, which are having very low cloud cover, and the dark ocean, which absorbs most of the incoming solar radiation, has the lowest albedo. Subtropical oceans. Yeah. And the value is around 0.01 or less. So this is just so that is with respect to latitude how it is changing. Now, if you look with respect to different seasons like winter and summer, so this all seasons are there. December, February is mostly winter. March, April, May is like pre-monsoon or peak summertime. And we have the monsoon period, which is June, August. Then we have the post-monsoon period. So even though globally we have four seasons like summer, winter, autumn, and spring. So generally, when we talk about seasons over India, we have like we generally say like winter, pre-monsoon, monsoon, and post-monsoon. So winter is generally characterized by December, January, February. Then we have March, April, May, which is pre-monsoon period, where we have like very high temperatures. So that is our summer generally. And then we have June, July, August, which is the monsoon. And then after the monsoon, we have the post-monsoon period, which is characterized by cyclonic activities and everything. So this is just with respect to India, I'm telling. So globally, we have like spring, winters, summer, spring, autumn, and winter, four seasons. So here, like during December, February, which is mostly the winter period, you can see over the polar regions there is very high albedo. So the red in the color bar basically shows high values of albedo. So you can see the polar regions are having very high albedo, and the oceans are seen as very dark regions with very low albedo. So these are the oceans which are very having very low albedo. And as we go to the March May period, during March May, the albedo is kind of decreasing. And during June to August, which is the summer period globally when you look at, so during the summer, it is having very low values of albedo because most of the snow or ice would have melted. And in the September November period, which is like transition towards the winter, we have like slightly the albedo starts increasing as the ice, snow, and everything starts to form. So this is how seasonally it varies. Winter we have the highest albedo, summer we have the lowest. So yeah. So the next one is desert regions typically exhibit positive net energy flux balance. Is it true or false? So what is basically the energy flux balance? So energy flux balance is basically the difference between the incoming solar radiation and the outgoing long wave radiation. So delta E, the difference between the energy flux, is given by incoming solar radiation or the radiation that is being absorbed by the Earth's surface, which is ES into 1 minus alpha, absorbed by the surface of the Earth, plus EO into long wave. So this basically gives you, so this is the absorbed solar radiation, and this is the outgoing long wave radiation. So the difference are, yeah, the difference between these two basically gives you how much flux is actually retained in the surface, kind of. So ES and 1 minus alpha plus EO long wave is basically gives you the energy balance at the top of the atmosphere. Yeah, so if you consider the direction into terms, generally the ES1 minus alpha it is coming towards the Earth, which will be positive, and the long wave radiation is going up. So if we take the sign into consideration or the direction also into consideration, it will be negative. So EO long wave will be negative, right? Yeah. So it is then eventually it will become negative. So it basically shows you how much is basically retained in the surface. So we know how the absorbed solar radiation is varying with respect to season and with respect to latitudes. We just saw that based on the albedo values. Now, what is happening to the outgoing long wave radiation? So the outgoing long wave radiation also varies with latitudes and seasons. So, which regions have the largest outgoing long wave radiation? So, high thermal radiation. Yeah, among the landmass, which region will be having the highest? Yeah. So the high thermal radiation is generally seen over hot deserts with little cloud cover. So the clouds actually It absorbs the outgoing long wave radiation, even though it reflects the incoming solar radiation. Yeah, yeah. So it kind of creates a warming towards the surface. So if there is high cloud cover, then it means like it will be more warmer in the surface. So it creates a warming kind of sensation. So hot deserts with very little cloud cover generally will have high thermal radiation. Since the cloud is not blocking the outgoing long wave radiation, it freely goes to the outer space. So hot deserts with less cloud cover have high thermal radiation, and cold polar regions with cold cloud tops. So the thermal radiation that will be going will be from the cloud top. So if the clouds are at very lower temperature, then the thermal radiation will be very less. The lowest thermal radiation will be going out from cold polar regions as well as from very cold cloud tops. So in case of hot deserts, the value comes around 270 to 330 watt per meter square, where and in case of polar regions, it is generally 270 to 330 watt per meter square. And over the, oh sorry, oh, in the polar regions, it is 100 to 170. Over the polar regions, it is around 100 to 170 watt per meter square. And over the hot deserts, it is 270 to 330 watt per meter square. And yeah, over the equatorial regions with very high cloud cover, over the tropics with high cloud cover, the value is 190 to 230 watt per meter square. And over the drier subtropics, it will be a bit higher compared to the tropics. So the largest is over the desert regions, or we can say the subtropic regions. Then um, in between we have like over the tropics, which is 190 to 230, and the lowest is over the polar regions, which is 100 to 170. Now, if you look at the so here we were talking about the net balance, which is the between yeah. So the net balance or the net radiative flux over the hot deserts, is it positive or negative, is what we were talking about. So here, if you look at the net radiation, so here we have the absorbed shortwave radiation, which is ES absorbed. So the blue line basically shows the ES into 1 minus alpha or E absorbed. and we have the long wave, which is the red line. So as you can see so the x-axis is basically latitude and y-axis is the energy with in watts per meter square. So over the equatorial regions, there is a net positive radiative flux, which is around 75 watt per meter square. So if you take the difference, it is positive. Absorbed minus outgoing is positive. We have 75 watt per meter square. And in the polar regions, the outgoing long wave radiation is higher compared to the absorbed short wave radiation. So there is more emission than absorption. So in that case, positive, and here it is negative. This is over the equator. And over the polar regions, we have around minus 100 to, around minus 100 watt per meter square. Now, over the desert regions, what is happening? So, deserts are generally at the subtropical regions, which is so if you look at like generally where these deserts are found, it will be mostly at the subtropical regions, which is 40-degree north or generally 40-degree north. So, over these regions, can you tell me what is the net energy balance? Is it positive or negative? Yeah. So the value is negative around minus 30 watt per meter square. So even though, so over these regions, we can see that there is high insolation. So even though there is high incoming solar radiation, high albedo and high outgoing long wave radiation due to low cloud cover and high emission temperature generally lead to negative net energy flux over these regions. So here what was the question? So the question was desert regions typically exhibit a positive net energy flux balance. Is it true or false? False. So the desert regions generally have a net negative energy flux balance of a value of around minus 30 watt per meter because of low cloud cover, high emission temperature, and high outgoing long wave radiation. Yeah. So the next question, the highest incoming solar radiation at the top of the atmosphere on June 20th is at which region? Highest incoming solar insolation at the top of the atmosphere on June 20th. So what June 20th is what basically? Is it which it belongs to? Yeah, it is summer season. So let's see how our Earth is actually during summer. So this is June solstice, or this is during June 2020. So the axis is actually facing the sun. So it is tilted towards the sun. Our axis is tilted towards the sun. So if you can see, the northern hemisphere is actually having 24 hours of day compared to the southern hemisphere, which is having 24 hours of night. And this figure basically shows you the insolation variation during different dates with respect to latitude. The x-axis shows the latitude, minus 90 degree to plus 90 degree. And on June 20th, you can see the southern hemisphere, which is basically denoted by minus 90 degrees south, is having zero insolation. The incoming solar radiation is zero. And as we go along the latitude, we can see the insolation is increasing. And the highest insolation is being received at which latitude? Yeah, pole, North Pole, right? So 90-degree north is actually receiving the highest insolation during June 20th. And during December 2021, if you see, it is reversing. During December 2021, you can see this is the location of the Earth. So this southern hemisphere or the axis is facing towards top axis is facing away from the sun. So in that case, the southern pole is illuminated by the sun 24 hours a day, whereas the North Pole is actually having 24 hours night. So during December, it kind of reverses, and the highest incoming solar radiation is received by minus 90 degree or 90 degrees south, whereas yeah, and the lowest is received by the North Pole, which is 90-degree north. And over the equator, if you see, the during summer and winter, the incoming solar radiation that is received by the equator remains almost the same. There is not much variation on the radiation that is being received at the equator. And the black line basically shows you the annual mean, that is combining both the seasons. So if you combine both the seasons, you can see the net incoming solar radiation that is being received by the region after you combine both the lowest summer and the highest summer value and the lowest winter value, you get a mean value of around 150 watt per meter square, whereas the equator, the values are equal during both summer and winter. So we have around 400 watt per meter square. And this dotted line basically shows you during an equinox what is the um, amount of solar radiation that is received. So during equinox, you know that the maximum amount of solar radiation is falling on the equator, and both the poles receive almost equal amount of solar radiation. Since the axis is basically parallelly facing the sun. So in that case, both the poles are receiving very less amount of solar radiation, and as we go along the latitude, we are getting the solar. As we move towards the equator, it is kind of increasing. So if you look at the insolation, yeah. So here the question was the largest annual daily averaged. No, not this question, right? Yeah, this one. The highest incoming solar insolation at the top of the atmosphere on June 20th is at. Now, can you tell me? Highest insolation during June 20th is at? Yeah, it is at the North Pole. And the lowest will be? Yeah. No, the largest annual daily average flux imbalance at the top of the atmosphere is found at that we discussed earlier actually. We discussed the different values of the flux imbalance, like over the poles, over the tropics, over the subtropics we discussed. Which region was having the largest value? You remember? Yeah. Yeah. So the extremely negative or the net highest imbalance was seen at the high latitudes near the poles. Yeah. Yeah. True or false? The decrease in snow cover at the high latitudes will decrease the negative flux imbalance values at these latitudes. If you decrease the snow cover, will it actually decrease the negative flux imbalance that we see at the polar region? That is the figure. Yeah. So if you look at this figure, so we have a net negative radiative imbalance over the poles, right? So suppose we are the snow cover is kind of decreasing. If we decrease the snow cover over the polar regions, what will happen to the absorbed shortwave radiation? Yeah, it will absorb more shortwave radiation, and the temperature will be more, and it will. So the difference is mostly due to the snow cover, which is actually not allowing the these polar region to absorb the incoming radiation. So if you decrease the snow cover, then more radiation will be absorbed. So basically, it will try to reduce the flux imbalance that we see at these latitudes. The land cover is contributing, or the albedo difference is actually contributing to the highest change in the flux over these regions. So if you decrease the snow cover, it will help us in decreasing the negative flux imbalance that is seen over these latitudes. So the answer is basically true. No. Now let's try to solve this numerical. A planet has black body emission temperature of 290 Kelvin. Black body emission temperature, or TE, is 290 Kelvin, but its surface temperature TS is 311 Kelvin. Assuming it has one isothermal atmospheric layer which absorbs a fraction of F of the infrared radiation emitted by the surface, what is the value of F? So if we are having an atmosphere which is not perfectly absorbing, if it is only absorbing a fraction of F, you remember the equation? What was the equation for when we have a partially absorbing atmosphere with an absorptivity of F? In that case, the this is the surface. The outgoing radiation will be F sigma Ts raised to 4. The absorbing radiation, the amount of radiation that the layer absorbs will be F sigma Ts raised to. Mm, mm. So here Ts and T epsilon are given. We need to find the value of F. Can you do it? So Ts is 311 is equal to 2 by 2 minus F the whole raised to 4 into Te is 290. So 311 by 290, 311 by 2, so this is 1 by 4, by 290, the whole raised to 4 is equal to 2 by 2 minus, or you can write 290 by 311, the whole raised to 4 into 2 is equal to 2 minus F, or F is equal to T epsilon by Ts, the whole raised to 4 into 2. 2 minus TE by TS into 2. It will be. F will be equal to 2 minus TE by TS the whole raised to 4 into 2. What will be the value? Value of F will be 311 divided by 290. Yeah, yeah. Will be 0.487. And from the options, which one will be? Yeah, this is the answer. Yeah. So now we are moving on to the next topic, which basically talks about the spectral distribution of the radiation emitted by the sun, earth, and the emission, the absorptivity and emission properties of the atmosphere. Yeah. So the question is, what is the relationship between the frequency and wavelength of an electromagnetic radiation? The frequency and wavelength of the electromagnetic radiation is basically given by nu is equal to C by lambda. C is the correct answer, where C is the speed of light, which is 3 into 10 raised to 8 meter per second. Nu is the frequency of the electromagnetic radiation, which is given in hertz or second inverse. And lambda is the wavelength, which is given in meter. So what will be the unit of this? C by lambda will be, yeah, yeah, will be hertz or second inverse. So this is the most basic equation regarding the wavelength and frequency of electromagnetic radiation. Now, which of the following statements are true about black bodies? A black body absorbs all radiation incident on its surface. A black body reflects all radiation incident on its surface. A black body is black in color. All black bodies emit different amount of thermal radiation for the same surface temperature. Which one is correct? First one. Yeah. So the black body absorbs all radiation incident on its surface. So black body emits the maximum, it is kind of an ideal body. It basically emits the maximum amount of thermal radiation for a given surface temperature because its emissivity is 1. And all black bodies emit identical amount of thermal radiation if their surfaces are at same temperature. So we know that E is basically given by sigma T raised to 4. The In case of a black body, so generally the equation is E is equal to epsilon sigma T raised to 4, where epsilon is the emissivity. So epsilon is basically the property of the body that we are considering. So the black body is basically having an emissivity of 1. So all black bodies which are having the same temperature will basically emit identical amount of thermal radiation. And the maximum possible or maximum amount of thermal radiation for a given surface temperature is generally emitted by a black body. Now, I think we have discussed this before, right? The value I forgot, around 0.6 or something, I guess. Based on the, like, since it has different land cover, different surfaces are basically having, yeah, I think it was around 0.6 or something. That I remember. I'm not sure. Yeah, I think it was around 0.6 or something. Okay. So according to Wien's law, what is the wavelength corresponding to the peak spectral irradiance of a black body with a temperature T of 300 Kelvin? Wien's displacement constant is 2.898 into 10 raised to minus 3 meter Kelvin. So, do you know what is Wien's displacement law? Yeah, yeah. Lambda max into T is equal to a constant. It basically gives you at a given temperature what is the maximum wavelength at which that body emits radiation. So the equation is given by lambda max into T is equal to a constant. In the question, T is given as 300 Kelvin and the constant value is also given, which is 2.898 into 10 raised to minus 3 meter Kelvin. You need to find lambda. So it will be lambda max is equal to 2.898 into 10 raised to minus 3 divided by 300. It will be, yeah, the answer will be 9.66 into 10 raised to 6 meter or 9.6 micro. The second one is the correct answer. Now, yeah, so this basically, the question is basically regarding the absorption and emission characteristics of the atmosphere. So, which of these factors do not affect the absorption and emission characteristics of the atmosphere? Amount of N2O in the atmosphere, amount of N2 in the atmosphere, Earth's surface temperature, frequency of electromagnetic waves. Okay, so let's go through each of each. So we know, like, so Earth's surface temperature, does it actually emit, does it actually matters? Like, does it actually influence the, yes. So Earth's surface temperature, does it affects, right? So this is wrong. And the frequency of electromagnetic waves. So does this basically affect the characteristic emission of the absorption of the atmosphere? Does it matter which wavelength is actually passing through the atmosphere? Yes, because it is transparent to the incoming solar radiation and it only absorbs the outgoing long wave radiation. So these two are not the answers. So now we have left with two questions. One is the amount of N2 in the atmosphere, and the second one is the amount of N2 in the atmosphere. So what does the gas molecules have to do with the emission and absorption characteristics of the atmosphere? So we know that there are different gas molecules in the atmosphere. Both homoatomic molecules are there, like N2 which is having same atoms. And there are heteroatomic molecules like NO, which is having different atoms. And the molecular structure of these atoms also differ. Like some is linear and some is planar or three-dimensional, etc. So in case of N2, it is like this. Two atoms which are um, connected like this. There is a molecular bond between them. So this is N2 is how N2 is there, and this is how O2 is present. And then we have like CO2. It is like this. So this is two oxygen, and on the center we have carbon. So this is CO2. And then CH4 is like this. Center we have C, and then 4 like this. So different molecules have different structures. The atoms are held together in the molecule by different bonds. So molecules, and also, so it can have different atoms. It will be homoatomic or heteroatomic. It can have different structure. It can be linear, it can be planar, or it can be three-dimensional. And it can also be polar or non-polar. Like there will be asymmetry in charge. So in case of two nitrogen atoms, which is N2, the number of protons and number of electrons will be equal. So it will be neutral. The net charge of the molecule will be neutral. But if you have different atoms present in a molecule, there will be mismatch in the number of protons and electrons. So it will have some charge. So molecules, there are some molecules which are non-polar, which means no asymmetry in charge. Like the number of positive and negative charges are equal. And then we have polar molecules, or which have a dipole moment. Molecules basically those which have a dipole moment. Are you able to hear me? I think I lost the connection. I think I lost the connection from my laptop. Okay, okay, just give me a second. Yeah, yeah. Just a second. Let me connect my laptop actually. I think I lost the connection from my laptop. Yeah. So N2 is basically is having a dipole moment. So since it is heteroatomic, it is having a dipole moment. So these in gas phase, these molecules are basically moving. Like in the atmosphere, we have a large number of molecules which are actually in constant motion. So these molecules, huh? Yeah, yeah, I'm trying to reconnect actually. I was just, yeah. Yeah, while reconnecting, I'll just tell you about the concept anyway. So basically, in gas phase, these molecules are basically moving in the atmosphere, and either they will be moving like linearly, or it can rotate about its own axis, like that bond, which is along with those bonds, they can actually rotate along its own axis, and also they can vibrate on their axis like springs, like a spring, like a mass on a spring. So these molecules are capable of having capable of undergoing different motions. So if a molecule has a dipole moment, like as I said, in case of heteroatomic molecules where there is an asymmetry in charge, these molecules can have a dipole moment. N2 doesn't have, but N2, which is a heteroatomic molecule, it does have a asymmetry in charge and it will have a dipole moment. So in case of molecules which is having a dipole moment, then it's the rotation of the molecules basically creates fluctuation in the electric and magnetic field, which can resonate in a certain frequency of electromagnetic radiation. So when the frequency of motion or frequency of rotation of these molecules resonate or become equal to the frequency of electromagnetic radiation that is passing through the atmosphere, the molecules will absorb the solar radiation. Is that clear? So the molecules which are having dipole moment or which are having a yeah, which is having a asymmetry, charge asymmetry, are capable of rotating on its own axis. So and it vibrates on its rotates or vibrates on its own axis. And because of this rotation, it basically creates fluctuation in the electric and magnetic field. And when the electromagnetic radiation of certain frequency passes through the atmosphere or pass through these molecules, the frequency of the electromagnetic radiation may match with the frequency of fluctuation of the solar radiation of the of the molecules, and at that time the molecules will absorb the solar radiation. So can you tell me in the question like which one will be the answer? We have nitrogen and we have N2O. Which one will be actually leading to change in the absorption characteristics of the atmosphere? Yeah. So the answer is N2O. Yeah, just give me a second. I'm trying to connect. Yeah. No, the thing is I don't have the presentation in my phone. It's in my laptop. Bishadit, I forgot what you were doing. What exactly you're doing? Uh, you're okay. You're doing PhD in atmospheric science. Okay. Which IIT? Okay. Triple IT. Okay. So now you're going through your coursework. Now you're like doing your coursework. Okay. Okay. What is your master's in? In atmospheric science only. Okay, you have your master's in physics. Okay. Okay, great. Oh my God, I'm really sorry about this. I don't know why it is not getting connected. Yeah, that is the issue. Okay. Uh-huh. Okay. I think I'll just rejoin once again from my laptop. Just give me 2 minutes. I'll just leave and then I'll try to rejoin. Yeah.